question has already given you VAN as a reference. Reference means angle 0. So if VAN is at the reference point 0 degree volts, that means VBN would be minus 120 degree, VCN would be plus 120 degree. We take it as a presumption in each question with the same rotation, 0, minus 120, plus 120. So the first part is the phase voltages. So VAN is 240 angle of 0 degree volts. Where this 0 degree comes from, it was instructed in the example question by myself. So you will always have a question telling you which one is the reference point. It is very important because the magnitudes for all three phase voltages would remain the same. It's the angles that changes. So the first part, we use a presumption that it has the same rotation, but we need to know the reference. So this is the calculations for the phase voltages. Part number B says calculate the line voltages. Well, we already got line voltage, which is 415 volts, but we don't know the angles yet. So we need to calculate three line voltages, VAB, VBC and VCA, three line voltages. In order for us to calculate the three line voltages, VAB, VBC and VCA, which is on the next page, we must use the equations which were the same equations that we have looked in the previous slides. So VAB is equals to VAN minus VBN, VBC is equals to VBN minus VCN, VCA is equals to VCN minus VAN. So all we have to do is to subtract the polar values in complex form. You can use the calculator, or you have to either convert polar form into rectangular form to perform the subtraction. So here I am using the simple basic methods. VAB is equals to VAN minus VBN. So VAN, if I convert 240 angle of 0 degree into rectangular form, that would be 240 plus J0 minus. We must use parentheses. It's important. Unless if you are solving the whole question using a calculator and you know how to do it. If you have FX9 and 1ES series calculator. But if you don't have, if you have a previous one, FXGT series, then you have to convert into a rectangular form. But make sure you use these parentheses. So minus sign, and if you convert VBN, which is this one, into rectangular form, that would be minus 120 minus J207.8. If we do the addition and subtraction, then it will give us the line voltage 415.66, angle of 30 degree volts. Now you might be wondering why we have 0.66 here, because the line voltage was given as 415. This is because of the calculation error. We do have a margin in these conversions. So when I did the calculations, I probably have not considered all significant digits. Or here in the phase voltages, if you do divide 415 divided by square root 3, that's your 239.6. So I have rounded up the number to 240. That's why my answer comes out as a 0.66 more. But don't worry, it is not about that little differences, but it's all about the calculation. So VAB 415.66 angle of 30 volts. This is the correct representation of the line voltage VAB. In order for us to calculate VBC, that would be VBN minus VCN. Again, we have to convert VBN into rectangular form minus VCN into rectangular form. Do the complex addition and subtraction. This gives us 415.66 angle of minus 90 volts. That's your VBC line voltage. Then VCA in similar order, VCN minus VAN. VCN must be converted into a rectangular form. That would be minus 120 plus J 207.8. Subtraction sign same. VAN is 240 plus J0 in rectangular form. After performing the addition and subtraction, we convert everything into polar form. That would be 415.66 angle of 150 volts. Now these are your 3 phase voltages and 3 line voltages. So part A and part B requires more time to actually do the calculation. And part C says calculate the phase and line currents. Since in the star connection, the line current and phase currents are equal, so basically if you can calculate the phase current, that would be the same as your line current and vice versa. Now part C might seem easier because in order to calculate the current flow through the impedance Z, we need to have the impedance and the voltage in order for us to use the Ohm's law. So we are going to use the famous equation V is equals to I times Z. But whenever you use the Ohm's law, you are calculating the phase currents, for example. In the star connection, the phase currents and line currents are equal, but in the delta connection, it is the other way around. So whenever we use the Ohm's law, we are using the phase values. Remember this point. So if you carefully look at the Ohm's law with the subscripts here, I'm calculating the current here, the phase current, IA. The reason I call it IA because it is not IAN, it is not IAB. It is simple IA because the line current is equal to the phase current. Whenever you use the Ohm's law, you are going to use all of the phase values. So for example, in this case, IA is the phase current. Then you must use the VAN, which is the phase voltage in line A, divided by the phase impedance ZA. And in this way, we divide the two values. We get our phase current or line current, which is 4.8 angle of minus 36.87 amperes. In order for us to calculate the IB phase current, we must use VBN over ZB. Similarly, IC is equals to VCN over ZC. Now you do know that the ZA is equals to ZB is equals to ZC because it is the balanced system. In the balanced system, all impedances are equal. But we are performing the divisions to get the same magnitudes, but the angles will be different. What if the impedances are different? values, then your magnitudes for each current would be different. This is called unbalanced system. At the moment, we are dealing with balanced star connection system. Now, part D says calculate the neutral current. I have deliberately put the neutral current because it is a star connection. And when we say the balanced system, which means all of the power would be consumed equally, there will be no difference. Therefore, the neutral current would be zero. I repeat, in the star connection, and if the system is balanced, meaning all impedances are equal, the neutral current would be zero. We need to prove it by applying the Kirchhoff's current law that says that the neutral current is equal to the sum of all currents, IA plus IB plus IC. So we have done the calculations for IA, IB and IC. If we all add together in the balanced system, the neutral current would be zero. So here IN is equal to IA plus IB plus IC. If we all add them together in a complex addition, it gives you approximately 0.001 plus J0 amperes. Hence, it is a balanced star connected system. You can also prove this concept on phasor diagram. That means you are going to add all the currents by drawing the parallelogram. So first you have the IA here. This is not asked in the question, but I have done it to make sure we are consistently applying the mathematics on phasor diagram as well. So here IA, IB and IC can be drawn using a protector and a particular scale for the currents. For example, 1 centimeter is equal to 1 ampere. Therefore, the length of each current would be 4.8 centimeters because we have 4.8 amperes. We can draw the length of the line by following the angle, which is minus 36.87 degree for the IA. So this is your minus 36.87 degree for the IA. Let's suppose this is 4.8 centimeter with a scale of 1 centimeter is equal to 1 ampere. Similarly, we draw